All right, here are a few more examples. These are focusing on how to take or find the derivative of an exponential function, as well as, or I should say, one with the natural base being e and the other being, any other exponential function with a base other than e. So, first thing you need to do is take a look at what we have here. Notice we have y equals e raised not just to the x, but the x to the fourth. So this is actually a composition of functions. So we're going to get a little bit more involved here. We're actually going to be using the chain rule as we use the rule for derivatives of exponential functions of base e. Now, the beauty of this one, it's just kind of a unique function. If you take the derivative of e, the function e to the x, it's just e to the x. So kind of kind of easy to do. We're not going to get into the proofs of these. There is a way of doing it by, using the definitions and so forth, and we're not going to do that. We're just going to use the results of these definitions. And so, quite simply here, all I'm going to do is I'm going to take the derivative of the outer function evaluated at the inner. So that's just literally recopying this, right? The derivative of e to the x is e to the x, but evaluated at x to the fourth, it's e to the x to the fourth. Then I'm going to multiply by the derivative of the inner function. So the derivative of x to the fourth is just 4x cubed. And all I'm going to do is just kind of multiply these. I mean, this is correct here, this times this, but it's usually more common or good form, whatever term you want to use there, to write the exponential function last here. So I'm just going to write this, and again, it's multiplication, it's commutative property of multiplication. I can write them in any order. So I'm going to write 4x cubed times e to the x, or e raised to the x to the fourth. Okay, so there's that one. Now this one over here again is you got to be careful here. This, when you have this written out, I picked that example here just to kind of address this. If there was, saying, no, wait, exponentials have to have positive bases, and this is positive because this exponent does not govern this -1 out here. It's like, just we'll kind of cover that up and just say, well, that's the base. That's my exponential function. 3 is the base, and 7x squared minus 8 is the exponent. And then I'm just multiplying by a -1 after I do that. Okay, so that's different. If there are parentheses around the negative, then we wouldn't have that because you have to have a positive base in order to be an exponential function. Okay, and the base is positive. It's just -1 multiplied by that positive base raised to that power. Okay, so that's a notational thing that can be confusing. So anyway, and that's the condition of the theorem here, right? Any positive constant a not equal to 1. So that's this thing here, which is in our example, the +3. Now, the only thing different here, the derivative of a to the x is just a to the x, but then I have to multiply by the natural log of a. Okay, again, we're not going to get into why we're doing that or the proof or anything like that. We're just saying that's the theorem. Let's use the result. And so here I go. I take that function here. I'm just writing this times a -1. And I could have put my negative out front. I multiply by the natural log of the base, which is 3. And then I just multiply by the derivative of the inner function, which is this exponent. So 2 times 7 is 14. The -8, that's just 0 there for my derivative for that term. So I just get 14x. Then I'm going to rearrange this multiplication. I'm going to put the negative out front. Then I'm going to multiply by 14. And then the natural log of 3, and then x. And I could have put the 14x here and then the natural log of 3. It doesn't really matter. And then I'm going to multiply by this thing. Okay, again, the negative is just the -1 times that. All right. And there you go. All right. Now, for the next one, notice now we had to use chain rule here and here. Here we have to use the product rule. Okay. So again, this is going to be the first times the derivative of the second. Remember, the derivative of e to the x is just e to the x, plus the second, which is e to the x, times the derivative of the first. So that's just 9, right, times x, subtract 1 to the 8. And then I just simplify that. I'm just going to rewrite, put the 9x to the 8th out front and leave my e to the x after this. Again, a lot of times if you have a common factor here, e to the x, we factor that out. We leave behind an x to the ninth, and we leave behind 9x to the eighth, and you just leave it like that. Okay. Generally speaking, the exponential functions are fairly easy to work with. They're not some, difficult derivative to find, and usually they're single terms and that sort of thing. So it's not a big deal. Okay. So there you go. There's your examples for exponential functions. And of course, there's going to be some that may be a little bit challenging, but I'm trying to get the ones so you understand the concept here without getting too bogged down in the algebra. Okay, remember to use the help features of my math lab, but if you do have any questions, you can send them to me and I'll get back to you. All right, thanks.